So we'll start with the first question. Dan Albedo's Ice Baby. So uh, before we start the question, I would like to mention that there are marks mentioned for each part of the question. That is only indicative for the directed team, and it's a general representative of how much you need to answer. Your time starts now. IIT Delhi.
No, read the question.
Oh, right. Sorry. Oops. I'll read the question. Sana scientists have run out of things to do yet again and are running Earth simulations in hope of magically predicting the lottery results. They run a million simulations to look at possible equilibrium states of the Earth. They soon forget about their initial lottery goals when they obtain a cool plot. The following diagram shows the results of their simulation, a collection of equilibrium states that the Earth climate system can exist in for a particular constant incoming solar radiation S0. Think of it as a scatter plot in the temperature PCO2 space, that is pressure of carbon dioxide, with each point indicating a combination of values of parameters of temperature and carbon dioxide pressure for which the climate system will be at equilibrium if it were to achieve them. So this is the graph. The climate system is highly sensitive to ice amounts because ice reflects quite a lot of sunlight, and more ice there is, the less sunlight is absorbed. A snowball state is when ice completely covers the planet's surface. A partial ice state is when you have some ice. The location isn't important and the exact amount will vary as a decreasing function of temperature, but the entire planet isn't ice covered, and an ice-free state is exactly what it says. With that in mind, let's take a look at a very interesting phenomenon represented by this graph. The first question. For the ice-free and snowball states, surface temperature values of the equilibrium states increase as their PCO2 values do, but for the partially ice-covered equilibrium states, the trend is reversed. Suggest a physical explanation for this. As a hint, here's a plot. The second question, according to this problem, is it possible to reach a partially ice-covered state P1 beginning from a snowball state or an ice-free state? Why or why not? Conversely, if the Earth was initially in state P1 and temperature or CO2 was changed, would the state of the climate change? Explain what is physically happening and in the process, figure out the nature of the equilibria along with the branches of the graph. The third question, although not particularly representative of our current climate, this model presents an interesting but frankly concerning problem. Most climate change solutions today talk about reducing emissions. If you were hypothetically in a snowball state and kept increasing carbon dioxide emissions past point P2, would reducing PCO2 level it was to the level it was at P2 be enough to return us to the snowball state? So that's all of your questions. Your time starts now. Oh, right. Any? Apparently not.
So in the first graph, we can see that they have mentioned that for the atmosphere to be in equilibrium, we have been given a plot of surface temperature and PCO2. So we can say that the atmosphere would be in equilibrium when the absorbed solar radiation and the radiated long wave are equal. We can tell this by the logic that the radiated long wave is roughly proportional to the atmospheric temperature, because the CO2 would absorb the radiated long wave and increase the atmospheric temperature. So we can say that during equilibrium, the surface temperature has to be equal to atmospheric temperature, and that's why the equilibrium point must be this surface temperature. So we can see that on increasing pressure, this plot is going down. So effectively, on increasing pressure, the temperature is decreasing, and that's what we observed in partially ice-covered state. On increasing pressure, the temperature decreased here.
Five minutes left.
It's wrong, whatever he said is wrong. Like the basic premise itself is wrong. What question is answering that even I don't know. Like yes, explaining why the middle valley may have negative slope. Okay, I don't know how. Fair enough, I did not get everything. But maybe started with the mathematics.
For the second question, let us say that we are initially in the ice-covered state and we start increasing the pressure. The temperature will begin to increase till it reaches P2. But after that, even if we increase the pressure, the temperature won't increase. So we won't be able to go into the partially ice-covered state. And also, if we are initially in the ice-free state and we decrease the pressure of CO2, the temperature will start decreasing until we reach that point at 290 surface temperature. And then again, decreasing the pressure further won't decrease the surface temperature. We'll have to increase the pressure to go in the partially ice-covered region. But at that point, it can again go into the ice-free state or the partially covered state. So this tells us that the equilibriums at 290 temperature and 260 temperature are unstable equilibriums. And conversely, if we were initially in the partially covered state, and let us say that the pressure was increased, then the temperature starts to decrease up till point P2. And again, we can't keep increasing the pressure further because it can go into the partially ice-covered state or the ice-covered state. So conversely, also we can't move from partially ice-covered state to ice-free or ice-covered state. Yeah.
It is what? Rubbish. Yeah, I know that one complains so much.
You have 2 minutes left.
The time is 6:09. Look at that. Yeah, we should plug in the projector afterwards because they are really not doing anything. I don't know when they'll come shit now. I think that is the island of something like this. I imagine. I would imagine that to go one of these ways. But they might have not. That is particular. Considered to do.
You have 42 seconds left.
So if we increase the pressure at point P2, we would move out of the graph, and because we move out of the graph, that state would not be in equilibrium. So the answer is no.
IT Delhi, time is up.
So, right, so starting off for the first part, so as we can see from the graph that was given below, when the earth is ice covered, it absorbs much lesser solar flux as compared to when it was, say, ice free. So what happens is, during the partially ice covered state, as the amount of ice reduces, earth begins to absorb more, which causes melting of ice due to increase in the temperature. So the trend gets reversed because as the partial pressure of CO2 here reduces from, say, let's go from point P2 to say P1. So as the partial pressure of CO2 reduces, the earth actually has to emit more amount of radiation. But the thing is, earth also now absorbs more amount of radiation, which causes melting of ice, leading to leading to the surface temperature actually being increased when the partial pressure of CO2 reduces. Moving on for the second part, as is visible from this graph, so when we are at say the snowball state, so suppose here in the snowball state, so in order to reach this particular partially
30
melted
seconds.
state, we from here we'll have to reduce the partial pressure of CO2. Now it can take two possible paths and we don't know which it will take. So we can't say for sure whether it will enter into the partially covered state or the snowball state. Same is true for this particular point here. So that's it. And for the last question, the answer would be no, because beyond P2 there is no equilibrium state from the graph. So therefore, by reducing this one, we cannot return back to the snowball state. We'll remain in the non-equilibrated state.
The time is up.
So for the first part, the trend is reversed because in the partially ice covered region, there is lower absorption by CO2, but there is lower albedo also. So reflected light is less, but there is also lesser absorption. So those are equilibrium conditions as same to bottom and above. Now for the second part, it is not possible to reach from ice covered or ice free to the partially ice covered conditions, partially ice covered equilibriums. Because let's say you reach till this point by increasing carbon dioxide and you move past it, then like during the ice melting phase, it will never be in this equilibrium because carbon dioxide won't reduce. It will jump to the above equilibrium condition. And similarly for the third part, it increases. Answer is no. you come back to
I
this
see your time
point
is up.
of the below one.
So for the first part in the ice flow, the snowball region, as we can see from the graph, as temperature increases, the absorbed remains the same while outgoing increases, and therefore the PCO2 increases. And for the partially ice covered part, as temperature increases, the absorbed part increases a lot more than the outgoing part, and so the PCO2 decreases. For the second part, yes, it is possible to reach a partially ice covered state beginning from both snowball or ice free state. And if the earth was initially in a state P1 and temperature was changed, it would still remain in the same state of the climate, because the equilibrium is stable in between and unstable on both the sides.
In the third question, if we increase temperature and go past point P2, then even if we reduce the amount of carbon dioxide, if we start at this initial point and we go past this point, then we'll then it won't be the same point anymore, and we can't reach the
Your time is
initial
up, IIT
levels.
Bombay. So now judge can clarify the teams, get clarification.
I have one question to IIT Delhi team regarding the plots or the hint we have given to you. What is this implying, that PCO2 of 100 and I can ask questions, right?
Yeah.
100 and 1000, the outgoing long wave radiation hardly changing. Is that information, how did it affect in your interpretation? Because I repeat the question, you see the hint plot given to you in two different, partial pressure of carbon dioxide. One is 100, the other is 1000, which is 10 times higher. Even if you pump up the carbon, your OLR is not substantially changing. They are following the same curve and same fashion. So that information, how did it influence in your interpretation of results? Did you use that information anywhere? Or how did you use it?
I actually didn't use that there is only slight change. I just used that the plot for PCO2 equal to 1000 was always below than PCO2 equal to 100. So the intersection point was below for the of the absorbed solar radiation and the pressure plot. I just used that fact to explain why the plot was decreasing in the first plot.
Now QMCs can come and present the answer. Oh, what do I do? Do I take it out? Do what? Should I show the slides or the... Okay. The board, no? You're using the board, right?
It's fine. Live streaming.
Hello.
At the bottom, it's on, it's on.
Okay. Yeah. But the first part is, okay, so you can think of it like this, right? You have a planet, there is some sunlight coming in, some part of it is going to be reflected, and some part of it is going to be absorbed and then re-emitted. So,
More the microphone.
oh, okay. Can you guys hear now? All right. So, this sum needs to remain the same, remain constant and equal to S in equilibrium, because if the planet is not heating up or cooling down, that means how much ever energy is coming in, it's losing. Make sense? All right. So now, if I we can consider two states along this line. Also, clarification, I'm not sure if the states are just, they're separate. We've not really mentioned whether you can transition between them, so it's not like a continuous go from one point to the next, that graph. Anyway, so here I have state, say P1 and P0. So this has a lower temperature, higher ice, and lower PCO2. It's the exact opposite for this point. So, okay, let's just simplify this. Higher PCO2, lower ice. Okay. So essentially the compensation that's happening here is that when you have a lower temperature and you have more amount of ice, this sum is mostly dominated by the reflected component. And if you want to make sure that this sum remains constant, you would like this component to be smaller, the re-emitted component to be smaller. That makes sense? So PCO2, carbon dioxide in the atmosphere, what it does is it reduces OLR. So if you want to make this small, you should have higher PCO2. So that's the compensation that's happening for equilibrium. The same thing for this point. Now, about the stability of states, if you start from this point, okay, I'm on the middle branch. Say I increase temperature. Now ice is going to melt, right? Now, if I'm increasing temperature, I've thrown the system out of whack. Like I'm going to melt more ice. And if you melt more ice, then you're allowing it to absorb more energy. Now, if it absorbs more energy than is going out, then it needs some way to get rid of that excess energy, right? But it has no way to do that, because if you're using all that energy to melt ice, and the more ice you melt, the more energy you're absorbing. It's like a vicious cycle, positive feedback loop. So this equilibrium is unstable for that exact reason. If I were to somehow change this balance, then it cannot exist on this branch. And if this is the graph that you're looking at, so the moment I change something here, it's going to either move to this branch or that branch. So these branches are neutral equilibrium, because the only only factor that's affecting your radiative balance is just carbon dioxide, because the amount of ice is changing is remaining the same along this branch, right? So if I increase carbon dioxide, I've mentioned that mechanism in the sheet. So OLR will decrease, it will be more energy will be coming in than is going out, so it will heat up. So you can move along this branch, that's all right. Now for the last part of the question, so this is the way you can traverse this graph, all right? This branch is unphysical. You cannot move along this, because I'm saying that, all right, if you were to be able to move along this, then it would essentially be saying that my temperature will decrease as PCO2 increases. That's not physical. That does not make sense based on the mechanism we've just explained. So this is not an option. This does not, if you start here, then you can stay here. But otherwise, there's no reaching here from either here or here. So the way this graph is traversed will be like here, then up there, then down like that, and then again. So this phenomenon is called hysteresis. You guys should have probably come across it sometime in 12th grade, I don't know. So this climate system exhibits hysteresis essentially. So even if you reduce carbon dioxide to the same level as it was here, you're not going to be able to reach the snowball. You're going to have to bring it all the way back here, and then you can sink to this branch. So that was the explanation for the question. Context, this is the hypothesis that has been put forward. So Earth has had multiple glaciations in its past, right? So this is the hypothesis put forward to explain the Neoproterozoic one. So yeah, this has actually happened, pretty cool to think about. If you guys have any clarifications, you can just talk to us after this is done.
Okay, so the next question number 2 goes to IIT Kanpur, and before the question is being shown to you, keep in mind that question number 2 and question number 3 that will be given to you guys are linked, and so the solution of both the questions will be given after both the questions are done at the same time. So you will not get the solution for question 2 after you've done question 2. Okay, the Empire Strikes Back. After the Death Star blows the Rebel base into oblivion, Rebel Commander Leia Skywalker is on the lookout for a new planet in which to set up operations. As a newbie Rebel and intergalactic climate scientist, the task has been entrusted to you, and you have identified 3 planets with potential: Hoth, Alderaan, and Geonosis. Initial reconnaissance missions conducted by the Millennium Falcon indicate the presence of greenhouse gases H, A, and G respectively in the planet's atmospheres. The archives are incomplete, and all available information on greenhouse gases is present in the top secret extra document in your possession. Hoth and Alderaan are quite far from the local sun and should be very cold as a result. However, the presence of H and A could indicate warmer surfaces as a result of the greenhouse effect. H and A are both like CO2 on Earth, well mixed such that pH by P and PA by P, where P is the total atmospheric pressure, is the same at all heights, non-condensable and very minor constituents of the atmosphere. Earth's atmospheric temperature profile is an isotherm, whereas Alderans is linear, increasing as a function of atmospheric pressure. The shapes of these profiles are maintained by convective processes and chemical reactions that are not affected by HRA. If more H and A were respectively added to the atmospheres of Earth and Alderan, they're still minor constituents, which would warm the planet up more. Which planet would warm up more and why? What happens to the temperature profile of the planet that warms up more after some time? After the Millennium Falcon's flyby mission, Han Solo is about to return to the rebel outpost at Dantooine, where the hyperdrive gets cooked. He has two nearby options for a quick landing so Chewie can fix it. The planet of Kamino, which has reasonably large oceans of water and an atmosphere primarily composed of nitrogen and oxygen, and the desert planet of Tatooine, with an atmosphere composed of nitrogen and oxygen. The temperature profiles are both similar to Earth's, with T increasing at P does. The coasts of Kamino are occupied by Kaminoans, so if the Falcon lands there, it must land inland. Plot the diurnal surface temperature variation of inland Kamino and of Tatooine, and in the process, help Han Solo decide where to land. Team IIT Kanpur, your time starts now.
Okay. So for the first part, the temperature profile for the hot planet is an isotherm, so which means even if we add more of the greenhouse gas, the temperature of the atmosphere will still remain the same. Whereas in case of the planet A, as we add more amount of greenhouse gases, the temperature should increase because as it was mentioned, it is directly proportional. So that was the first part of it. So as we can see, in the case of hot, after adding greenhouse gases, the temperature of the atmosphere is still the same, whereas in the second case, the temperature of the atmosphere increases. So if the temperature of the atmosphere increases, the atmosphere should actually like emit more amount of radiation. Now, where does the atmosphere get its radiation from? It should get it from the Earth. So, Earth should actually emit more radiation in order for the atmosphere to be maintained at a higher temperature in planet A. And apart from this, because of the greenhouse gases, there will anyway be an increase in the Earth's temperature because of the the absorption of OLR. So, what happens is, in case of both the planets, the planet will heat up because of the greenhouse effect. But in the case of A, it should heat up even more so that the atmosphere also gets heated up. So that is what would happen to the temperature. That is what would happen. So hence, planet Aldebaran would actually warm up more. Okay. So the second part we'll discuss later. Okay. For the second part of the first question, what happens to the temperature profile of the planet that warms up more after some time? The planet that warms up more is here Aldebaran. So as the planet warms up more, the temperature profile will change as shown because now the P will be more, so the temperature profile changes according to that graph.
You have 5 minutes left. You have 2 minutes left.
So the thing is, if you look at, we think Kamina is more suitable than the second place, the one that starts with the T. I can't pronounce it. So, yeah, and the reason is dependent on the fact that the planet that starts with K has water, and so the variation is not as much as it is on the desert planet because land heats up faster than land heats up and loses heat more quickly now. So during the daytime, your land heats up, and during nighttime, when your land it loses heat, you basically have the warm the temperature of the air above the sea. What do you call it? It's still warm now, so you have your so you have your sea breeze coming in, which keeps your land warm.
You have 30 seconds left.
Basically, because of the land breeze and sea breeze, like there's less temperature variation. So, like,
So which makes it more suitable to land.
IIT Kanpur, your time's up.
So basically, for one of the planets, the temperature is linear function of pressure. So the density remains constant. So the planet for which the density remains constant, then and for one of them the density decreases with pressure when the temperature is constant. So for the one which with density decreases with height, that will have low. So the greenhouse effect of the gases at the higher level will be lesser, and the ones at the lower level will be higher. And for the one where the density is constant, it will all be the same. So for the planet where the temperature is a linear function, the temperature will be higher, and when the temperature increases, then the emittance level increases, and due to the higher emittance of that, due to higher emittance, the temperature decreases again. Like when the surface temperature increases, the emittance of the greenhouse gases increases, and the temperature falls back, and as a result, it oscillates back and forth. That is our idea.
So in the second question, the place where more oceans are there, the thing should land over there, because there are more diurnal variations in the place where more deserts are there. This is because when you have a sea, you have this sea breeze and land breeze which can moderate the temperatures. This is possible as temperature is proportional to the pressure, and convection can happen. And so sea breeze happens in the morning, and the cool air from sea goes to the land.
You have 30 seconds left.
So the cool breeze from sea goes to the land and moderates the temperature on the surface inland. And during night, cool breeze from land goes to the sea, and it moderates the surface temperatures that way. So the diurnal variations of the planet will be like smaller.
IIT Bombay, your time's up.
Okay, so for the planet A, since the temperature is directly proportional to pressure, the density will be constant, and adding more of A gas on Aldebaran will not cause any effect. But on planet H, since the density is not constant, if we add more of H gas, the temperature will increase in the regions which has high pressure, which is near the planet H, and so it will get warm up more, and the final temperature profile of the planet that warms up more after some time is drawn over here.
So for the second question, the second planet is having more variation in the temperature, and the first planet is not, because of the ocean and because of the sea wind and land wind, which is blowing in the daytime and the nighttime, which basically acts as a cooling. It basically cools the land in the daytime, and heats it up in the night time. So
IT
the
Bombay, your
variation
time's up.
So our answer is that Hoth will warm up more, and that is because in the other case, in Alderaan, the temperature is it's linear with increasing function of atmospheric pressure. So the greenhouse gas that we add will be at a higher temperature, and hence we can say that it will radiate more for all the long wave it will absorb.
For the second question, this is the graph of planet K and this is the graph of planet D. I don't think so the land breeze and sea breeze will affect the problem because it is given that this is inland. Camino will have a later peak because water reflects light more, and it has planet D will have an earlier peak because land does not reflect light as well as water.
IT Delhi, your time's up. Now I would like to ask the judge if they require any clarifications from the teams.
Yeah, so well presented. I have one clarification required from the one who presented, IIT Kanpur, right? So, so in the planet H and A, which situation is more closer to Earth? Which planet is more, the situation of which planet is more closer to what you find in Earth, H or A? That means Hoth or Alderaan.
Which is closer to Earth.
Huh.
Okay, I would say that it would be Alderaan maybe, because pressure increases the temperature.
Okay, so what about the temperature?
Temperature of?
The Alderaan. Does that anything resembling Earth or?
No. I'm not.
Okay, second question I have. From the hint, did you use any point regarding the partial pressure to the pressure ratio in developing your answer? If you used that hint, what hint how you used that hint? There was a hint given PA by P and PH by P. Did you use that in your interpretation?
We use that hint in finding how the profile will look after adding CO2.
You used it?
Yes.
And you ended up in this profile?
Yes.
Good.
That's all. Slight change of plans. The QMC will be coming to explain this question. And you'll get, the question 3 will be yours.
Okay, super quick. This is how it works. All right. So you have this is your atmosphere. It's composed of layers. All right. So now when you're talking about radiation that's escaping the top of the atmosphere, you have some contribution from this layer, some contribution from that layer, so on and so forth. Now this we've given that the profile of pressure is decaying with height, so it looks something like this. So you have like a higher amount of gas here, followed by lower levels. So now, when you add more carbon dioxide, so these lower layers, because they already have more greenhouse gas to begin with, they're going to start acting like closer to black bodies, right? And if these layers start to act closer to black bodies in which they're absorbing everything and emitting according to their temperature, so the behavior at the top of the atmosphere starts to get decoupled from these lower layers, because this level in the atmosphere, these levels in the atmosphere, if they start to act like black bodies, then this will absorb everything that's coming from here. This will absorb everything that's coming from here. And what's coming at the top is now only decided by these layers. So essentially what happens when you add more greenhouse gas is there's a concept of an effective emitting layer, all right? That layer is going to sort of shift upwards. It will shift upwards here because the greenhouse gas is a minor constituent of the atmosphere. So when it shifts upwards, you have a different, so the temperature profile for Hoth is constant. So if this is height, this is temperature, it looks something like this. So now when this upward shift happens, it's still radiating at the same temperature, right? Essentially, because temperature is constant everywhere. So no matter what you do, how much outgoing long wave radiation is escaping at the top of the atmosphere is going to remain constant. So you don't have a greenhouse effect. How does a greenhouse effect work? You have to reduce OLR at the top of the atmosphere, and that will cause an imbalance and a heating up, right? So with Hoth, you don't really have that option because whether the radiation comes from this layer or this layer, all the same. Now for Alderon, it does make a difference because here your temperature profile looks something like this. So now if my lower layers are getting blocked out, this higher layer is now contributing more to it because you won't have a lot of contribution from the highest layers, you'll have it somewhere from the middling layers because they have enough gas there so they can absorb and emit sufficiently also. Now here, the temperature is lower than at this point. So here, they're going to be, when this effective emitting layer shifts up, you're going to have lower OLR. And that is basically how the greenhouse effect works even on Earth. So when you increase carbon dioxide, this layer shifts up, the temperature is lower over there, less OLR, and that's how that imbalance happens, and then you sort of end up heating up your planet. So the temperature profile now will shift such that, okay, now I have this over here, I will extend this. So this will sort of start to look something like that. Essentially, that's what's happening. Second part of the question is, okay, sea breeze and land breeze won't be that much of a, it will contribute, yes, but we've mentioned that it's inland, far inland, so you're not going to have a much of a contribution from there. Essentially, what happens is you have water vapor from the atmosphere. You guys know water vapor is a greenhouse gas, right? So that will essentially radiate, you'll have back radiation from the water vapor layer to the surface during the night, which is what makes the temperature oscillation for the watery planet lower magnitude than in the desert planet. That's the answer.
This is the solution slide for the previous question. So we'll move on to the third question. Third question is directed to team IISc. Running away to Geonosis. First question. Geonosis is very close to the local sun, and as per the last records of it in the archive from nearly 1 billion years ago, it had an atmosphere composed only of greenhouse gas G. The partial pressure of gaseous G at any level is also the atmospheric pressure at that level, and massive oceans of G. G is a condensable gas, and through convection, the temperature profile of the atmosphere always follows something called a moist adiabat, which means that at every level G is saturated. Equation of the moist adiabat is given here. The temperature increases with pressure and therefore decreases with height. P naught and T naught are some reference pressure and temperature on the Clausius-Clapeyron curve. This plot shows the total outgoing long wave radiation, OLR, at the top of the atmosphere as a function of the surface temperature for Geonosis. Assume that at 180 Kelvin, which was the surface temperature 1 billion years ago, there is almost no gaseous G, and that this amount increases exponentially with temperature. Why does OLR plateau out at higher temperatures? Second question. 1 billion years ago, the solar insolation of the local sun was S1, near about 160 watts per meter square. However, solar luminosity has since increased and insolation has now changed to S2, about 280 watts per meter square. What might have happened to Geonosis in the interim? Is equilibrium possible with this situation? Why or why not? And what might make it possible? A hint, we have assumed that G absorbs uniformly at all wavelengths here, but that is in general not the case. Something similar is hypothesized to have happened on Venus with initial oceans of water. If the number of oxide minerals increased on the surface during this interim period, can you guess why? Which planet do you choose finally for while making your recommendations, consider only whether the surface will have a habitable temperature or not. The rebels can arrange for everything else. Your time starts now. Has started.
Could be any pressure like it relates, it has T naught also. Some limit. see our fans. It's a bit lagging. Very lagging. I will do something. Where is the camera, guys? Should we switch? Sure. This is the 6-9 shit. 6-9 shit. Can it stop 2 minutes and 9 seconds and then 1 minute 69 seconds left? We can stop it at 2 minutes and or 5 minutes and 9 seconds. 4 minutes and 69 seconds left. Yeah, we can do that. Here now. We can. No, we should do that actually. That's fine. Oh, shit. We can do that. It's fine. They don't need to see it. True, true. Lot of stupid.
Equation as you can see, the temperature actually increases with pressure. So at
5 minutes.
Yeah, as the height keeps increasing. Okay, so as the temperature increases, there's increase in pressure. So the greenhouse effect increases, and as a result, at some point there will be like such a thick layer that none of the radiation will be able to come out of it. Like all of the radiation will be trapped inside it, and then the only OLR that was original, yeah, the last layer, the OLR corresponding to the last layer, only that will remain, and all of the remaining LOR will be like just OLR will be just trapped between the layers for the first part.
Like, yeah, this is because the atmosphere of the planet Geosis is mostly composed of greenhouse gas G. So that's the case. एक पॉइंट पे पीक कर जाएगा, उसका रिफ्लेक्शन ना उसका रिफ्लेक्शन हमारा वो क्लियर तो एक पॉइंट पे पीक कर जाता है, पर सरफेस टेंशन जैसे जैसे ये बढ़ रहा है दैट इंक्रीज सरफेस टेंपरेचर, तो इट विल कीप ऑन So for the second part, since we know that the OLR peaks with a certain amount of saturates with certain amount of temperature, during the process of going from S2 to S1 to S2, since the amount of energy received to the planet keeps on increasing, if at any point in this process it peaked the OLR, like it saturated the OLR thing, the temperature of the planet will keep on increasing and increase very rapidly. So, that also relates with the case with the Venus, which is it might have had ocean. Since we can think of this greenhouse gas G as kind of water vapor, which is condensable gas and also greenhouse gas. So this explains the case with the Venus.
And this increasing temperature might have caused oxidation. I mean, favored oxidation in Venus. It might have catalyzed that process. And since this
2 minutes.
Yeah, and since the temperatures are very unstable over here, it's increasing rapidly. We don't think landing in this is safe. So we would land. After land.
So we believe the final planet to land upon is the Camino, because since it's a desert planet, the greenhouse effect there is lower. So the overall temperature, even though the variation of temperature is higher, we
30 seconds.
It's a water planet, so Camino is a water planet, so we need to land over there because the temperature variation is very low, and yeah, that's the most feasible one.
ISC time is up.
Okay.
Hello.
So in the first question, we have an equilibrium between G liquid and G gaseous. As the temperature increases, we move towards the right in the equilibrium and we get more gaseous G. This will increase the OLR, but on further increase of gaseous G, the density will increase only on the bottom layers and the effective emission layer on top will still give out the same amount of OLR. And therefore, because it is an effective emission layer and the bottom layers will act as a black body. Therefore, the OLR will plateau at higher temperatures. For the second question, the solar insolation increases. There are two hypotheses we have. One is that it could be because of increased solar activity in a solar cycle. And second is that stars usually have a fuel, and let's say that the hydrogen fuel ran out and we're now using helium as a fuel. So it could be possible that this is why the solar insolation has increased. In this increased solar luminosity, 280 watts per meter square is above the 250 watt per meter square OLR that is possible, and thus we cannot have equilibrium because the input and the output cannot ever be equal. And to make this
30
equal,
seconds.
To make this equal, we'll either have to add another greenhouse gas or we'll have to.
For the Venus case, water vapor will act as the gas G, and so the eventually, because there can be no equilibrium, so all the water vapor will run away and there will be just oxides. Finally, we'll choose the planet Hoth, because Venus right now, because Geonosis and Aldebaran cannot be chosen. Aldebaran, we proved it last time, and Geonosis, obviously all the water runs out.
IIT Bombay time is up.
So in the first question, the amount of radiation emitted will grow as per T to the power 4 at the surface, but the amount of greenhouse gas is growing exponentially. So at one point of time, this term will start to dominate T to the power 4, and that's why we are saying it will plateau out. In the second question, if we take that assumption, then an equilibrium is not possible because the OLR plateaus out at 250, but the sun is emitting 280 watts per meter square. But what actually happens is that it will start emitting more in shortwave radiation, and so eventually an equilibrium should be possible. And as for the recommendation, we'll say definitely not Geonosis if we take that assumption, because its temperature will continue increasing. So we'll say planet A purely because it is same as planet Earth.
IIT Delhi time up.
Okay, so in the first question, the amount of G is directly proportional to E raised to T. So as temperature increases, G increases. And with increase in G, it saturates in the atmosphere. So then the whole Earth will become like a black body. Then all the energy coming out would be same as the energy leaving. So it would, the total energy going out would be the same as S, which is emitted by the sun.
Now for the second part, so first thing is, as we can see in this OLR versus temperature curve, it caps out at 250. So, but then the radiation now, incoming radiation has now increased to 280. So now there is no way for geonosis to attain equilibrium, so it will just keep on heating up. And now the oxide minerals will increase because oceans will dry up, causing the minerals to come up. And lastly, we'll choose planet H or A depending upon the isotopic
IT Kanpur
temperature
time
of
is up.
H.
Now the judge can ask for clarifications from the team.
Have one question to the team, first team who presented it. So the question is, what G resembles here, carbon dioxide or NOx? What G resembles in Earth system, methane, water vapor, carbon dioxide or NOx?
We think it resembles water more because again it's condensable and it stays in liquid state also.
Okay. The next question is that there was an assumption hint given that G absorbs at all wavelength equally. Have you used this assumption in any of your interpretation of the results? Why they have given that hint? G absorbs at all wavelength equally. It is given as a hint.
Yes, sir.
So why they have given that hint and what part that is useful in these questions?
So sir, when we say that like at the lower level,
Can you keep the mic?
Yeah. So at the lower level, the greenhouse effect kind of peaks. It acts like a black body. So we use the assumption that it absorbs all the wavelengths, like a black body absorbs all the wavelengths.
Well, for that reason, it should absorb in all wavelengths. It can be in any wavelength for this to happen. Okay. Yeah. Thank you.
So the QMCs can come and explain the answer.
Okay, this is the last you guys will see of me, I promise. New QMC explaining the last question. Okay. Yeah, I think you guys actually mostly got the concept. So what's happening is this is different from the Hoth and Alderaan case in that when you move to, okay, we'll do it like this. The layer diagram from before. Now when initially you have contributions from all these layers, but as the amount of greenhouse gas starts to increase, you're only going to get contributions from higher layers. That's absolutely correct. So what sets the limit on where this radiation can come from? So remember, if the amount of gas is too low, then there's nothing there to absorb. If there's nothing there to absorb, there's nothing there to emit also. So you have a certain characteristic pressure from which it's like a balance. You have enough amount of gas so it can absorb everything that's coming in below, and there's less above so that whatever this layer, this characteristic pressure layer emits, it passes through mostly unabsorbed. So now the difference between this and the Hoth and Alderaan case is that here temperature is a function of that pressure. So that characteristic pressure is not changing. So when you reach the limiting case where all of the radiation is only coming from the characteristic pressure layer, its temperature is fixed by the Clausius-Clapeyron equation. So you're always going to have the same OLR after that. That is correct. Now, the next part, what happens when you have higher solar radiation than OLR? I mean, we've done this a bunch of times. The oceans will evaporate, yes, so you'd expect all of G to be in the atmosphere, and there's no way you can reach equilibrium like this because there's always going to be more coming in than is going out. How there can be equilibrium is if it's a band gas. So once temperatures hit a high enough value, they're going to stop radiating in the band that this gas absorbs in. So the greenhouse effect is no longer valid. This can somehow, it can reach equilibrium from there. The mineral question, okay, so on Venus, once all of your water vapor is in the atmosphere, a lot of it is present higher up. And there you'll have ultraviolet radiation that will split it into lighter hydrogen and oxide. Now the hydrogen, because it's so light, it will escape the atmosphere, and the oxide, highly reactive oxygen, will go to the surface and react with minerals there to give you a lot more oxide minerals. Okay, I'm not sure if that was super clear, but if you guys take away anything from this, I mean, it should be that, okay, look, we are really, really super lucky to be on Earth, because a lot of things could have gone wrong on here that would prevent life from happening, but they didn't. So just sort of appreciate the fact that all of this stuff is happening, all of this needs to work out and be in tune for, you know, habitable conditions to exist. All right, cool, that's that.
Thank you, Medha. Now we move to our final question. One bubble at a time. IIT Bombay, this is yours. Scientists have found an Earth-like planet covered by lakes and large oceans. Here they found two kinds of bacteria and bacterial mats present in many lakes. These two kinds of bacteria are unique in ways in which they respire. One is green in color and carries out photosynthesis, this cyanobacteria. Depending on light levels, this bacteria switches between anoxygenic, when light availability is low, and oxygenic photosynthesis, when the light availability is high. And it stores a part of the energy produced as glycogen. When it doesn't get light, it uses the stored glycogen to carry out anaerobic respiration, which is sufficient to last until the next instance of sunlight. It does not use oxygen and ferments the glycogen into energy, some byproduct, and CO2. The other is white and translucent and carries out aerobic sulfide oxidation to generate energy, SOB. Both bacterial species are motile, capable of moving within these mats. The equations are just for you to know what resources are necessary. Please ignore the exact quantities required for the reaction. Note the following. Oxygen produced by oxygenic photosynthesis is in dissolved state and is isolated to the area where it is produced, from where it diffuses at a slow rate. Sulfur is present at the bottom of the mat on the floor. The H2S generated by this sulfur diffuses from the bottom to the top. The water above the mat has low levels of oxygen, which diffuse into the mat. Assume that CO2 is not involved. Bacterial mats are optically dense. Question 1. What would you expect the cross-section of the mat to look like at different times of the day, given the state of the mat at hour 6? Give the states at hour 12, 16, 20, and 0, assuming a standard 24-hour day-night cycle. Roughly mention changes in the 4 parameters, AP, OP, O2, and S total, to justify your mat cross-sections at each hour. Question 2. The planet's rotation is slowing down due to effects of tidal friction. The tidal bulge in the oceans sloshing back slows the planet down. Assuming that the only way oxygen can leave mats is diffusion, what implications does this slowing down have for oxygen levels in the mat and the atmosphere? Your time starts now. geophysics. It was deep. We can make that for deep. A lot of them would have been able to solve that. Like I tried the ISC, you guys would have gotten it. Tried the ISC, people would have gotten it because physics. All of these are physics. Not directly to them. This is they're so done. So done. Want to go to the benches and look at what they're doing. Want to go to the so they yes. The guy's stuff needs to compensate somehow. You see that what it will tell you after what happened. Faces, you know, they can, but Who is this? IIT Bombay, right? Oh, yes.
5 minutes left.
See you solving it, identity understanding the solution. Something happens, they move.
So in time 12 to 16, the intensity is very high, and therefore we will have aerobic respiration photosynthesis go down, and oxygenic photosynthesis will be higher. Therefore, the concentration of oxygen will increase. So initially at T equal to 12, you can see OP is higher and AP is lower, but oxygen is not yet being produced. When we go to time equal to 16, then oxygen concentration will have increased. Due to aerobic oxidation, the concentration of H2S will constantly keep decreasing, and therefore the
So at time equals to 0, we are given that it is completely dark. So the overall concentration of H2S will increase because there will only be because none of them are using it. OP and AP both will decrease because there is no use of oxygen. Then the O2 line will almost be vertical because it is all being diffused. S total will increase in the cyanobacteria region, but in the SOB region it will be the same.
And the case of 20 is same as the R6 because the intensity is low at both the times, so they would be same.
Just that in the case of 20, the H2S has already diffused and has been used up to generate the energy.
2 minutes left.
That is all. And for the second part, if the rotation speed of the if the rotation is slowing down of the planet, the diffusion of oxygen will reduce. Just a minute.
You have 30 more seconds. IIT Bombay, time's up.
So the graph we've given was for R6. At R12, since there's high intensity sunlight, there will be more oxygenic respiration instead of anaxigenic photosynthesis, and thus the oxygenic photosynthesis line will shift to the right and anaerobic will shift to the left. Similarly, because H2S will not be used that much in the layer of the cyanobacteria, H2S will shift to the left. Now, when time reaches 16th hour, what will happen is that the oxygen that was at the top inside the lake or water body, the oxygen will be almost depleted, and thus anaerobic photosynthesis will again start to dominate. And after that, throughout the R20, we'll see a similar case as R6, but with more anaerobic respiration, since there's again less oxygen remaining. And at R0 will be similar to case, no, it will even have more anaerobic respiration and more amounts of sulfur, H2S being used in the cyanobacterial layer.
You have 30 seconds left.
Yeah, so at 12, OP. So at R12, as you've seen that oxygenic photosynthesis will increase from 6, but at R16, the oxygenic photosynthesis will decrease and anaerobic will increase because oxygen has depleted. Yeah. That's about it. And also it will,
IIT Delhi, time's up.
Okay, so the effective gravity will increase by this formula as the rotation decreases. And since oxygen diffuses from the top, since gravity increases, it will diffuse slower. That's the second question.
So hence, yeah, so in the mat, the oxygen level will decrease and the atmosphere will increase. So moving on to this one. So what will happen is, okay, from 6 to 12, the amount of sunlight will increase. So therefore, the AP will decrease and OP will increase. Whereas from 12 to 16, sunlight again decreases. So AP will increase and OP will decrease. And similar kind of trend can be observed. Whereas for sulfur total, what will happen is in the lower regions, because it is converting to H2S, the sulfur will decrease. In the middle region of cyanobacteria, the trend will be similar to that of the AP, Whereas in the normal SOB region, the sulfur will always be increasing.
IIT Kanpur, time's up.
So, if the Earth, so we are trying the second part. So, if the Earth stops moving, then one side will only face the sunlight and the other side won't face the sunlight. So, the part where it faces the sunlight, the mats will have, we assume that, like we think the mats will have some kind of structure where the top of the mat will have cyanobacteria producing oxygen, which doesn't go out of it because now no longer there are tidal forces. So now, since the bacteria are motile, so the bacteria which do sob will come and replace the position of cyanobacteria in the light region and carry out its process. In the meanwhile, cyanobacteria uses do anaerobic respiration, and then the cycle continues.
IC Bangalore, your time's up.
We lost 10 seconds.
Okay, continue.
So in the dark region, since now coming to atmospheric oxygen, darker region will utilize the dissolved oxygen in the water.
Time's up. Judges, do you want any team to clarify?
There was a hint question on how the diffusion working between oxygen or amongst oxygen and hydrogen sulfide. So have you noticed that information is any relevant to finding answer to this question, especially the second question?
So, sir, for the first question,
yeah.
So it says that the sulfur is present at the bottom and we get H2S. This is required because in all three reactions we're only using H2S as a reactant, and it will be consumed all the time. So we need to produce H2S somehow.
Okay.
That's why we need it. For the first part, we have so for the SOB, it has aerobic oxidation and oxygen is used. So and since oxygen produced stays where it is, thus we need to somehow diffuse oxygen into the mat from above, which is given by the third point, which is that some low levels of oxygen are diffused.
Okay, good.
So yes.
So the what about the second question? This has anything to do with the second question that is asked?
So,
I mean,
sir,
the tidal forces versus
yes, sir.
length.
Sir, in the second question, so we can assume that that the oxygen produced due to photosynthesis is locally stays, but the oxygen above due to the water, it says in the third point that the oxygen diffuses from above. That does not.
What connection that tidal forces comes to the biochemistry we are discussing? What will be a connection?
Sir,
tidal force is physical, right?
Yes, sir.
And biochemistry is biology and chemistry. What way they are related in all these?
So it's only about diffusion. If the planet's rotation slows down significantly enough, then the diffusion will be lower.
But diffusion is molecular here, right? Mostly kinematic, not gravitational
yes, but,
forces.
So it's not about the gravity,
Okay,
but the rotation of the planet.
Okay, yeah, good. Thank you.
Once that's done, we'll call Berry Moger to come and explain the solution.
I do have some overall comments. Can I?
Oh,
take one?
yeah, sure.
And first of all, I congratulate all the team. I know this is it's a toughie. It's all people might be coming from various background, some fundamentals in science, but you all have done very well with your capacity, and I appreciate that. Generally, all the teams have done equally good, and so good effort. And these are very really mimamsa means thought-provoking questions, right? Good, all about effort and congratulations. Yeah. Thank you.
Thank you, sir. Over to you, Berry.
Yeah, so
Where do I start? So the movement was a very important part of the question because resource limitations will cause the bacteria to move around in the mat. So I think at the R6 I've mentioned that the amount of AP being carried out is very low. So that's because, let me just get a chalk, I'm sorry. Yeah. So, yeah, so because you have this on top, and another thing is this guy is translucent. So the light passing through, even if it's low, it was low sunlight, right? Even if it's low sunlight, the amount of sunlight reaching this guy is it's lower than what is at the top of the mat. Okay, and this is at R6. Let's say at R12. So it has just reached a period that has high sunlight. Okay, but because SOB is still at the top, high sunlight would mean some intermediate amounts of sunlight. So there would be higher amounts of AP being carried out, and oxygenic photosynthesis will initiate happening. And also note that because AP uses up H2S, but OP does not. It does not need H2S. So when AP is being carried out from our 6 to R12, it's essentially using up all the H2S that's coming from the bottom of the mat. So, and SOB only uses H2S. So what would happen when all of this H2S is now being depleted here? So essentially something like this. So there is SOB wants H2S, but it's no longer getting it because H2S can only come from the bottom. So the only thing it can do is move below. So it moves below, and this guy has to move up to be able to do oxygenic photosynthesis, and it's now getting high sunlight because the SOB is no longer on top of it. So it's directly getting high sunlight. So now let's say at R16. R16 is when it has been exposed to high sunlight for quite a long period of time. So there is a insane increase in oxygen in that layer, and it like diffuses to both sides. So there is what is important to mention is that there is a change in the profile. Let's say this is SOB. Yeah. So there's an increase in oxygen. So SOB wants this oxygen increase and also the H2S because it uses oxygen and H2S. So there is also an incentive to move here. And as you move on in the day with R20, no, okay, it's fine. Yeah, at R20 would be, I forgot, it's low sunlight, right? Yeah, so SOB wants to move up for the low, this thing, and this guy is doing AP because it's low sunlight, and there is an H2S gradient, and the H2S has been used up by the SOB. So now there's a switch in places. So they change their profiles again. And at R0, this doesn't change. This remains as a flipped profile. And now the day starts again. So it's a cycle. So, and for the second part, so when the Earth's rotation slows down, what would happen is that the day length cycle would change. So that is important, that the bacterial mats are exposed to more amounts of sunlight. So that is something that was important. So more sunlight means there is longer periods of time when this insane increase in O2 is happening. So there is more O2 diffusion outside of the mat. So what the implications of this was on modern day Earth. Do you guys know about the Great Oxygenation Event? Yeah. So these mats were present all over Earth, and because the moon was slowing down the Earth's rotation, the period of day length was just long enough for oxygen to start actually leaving these mats from bubbling, and that led to increase in oxygen in the Earth's atmosphere, which led to us being able to exist here right now. That's it.
Thank you, Barry. Can we have a round of applause for all the participants and everyone? That was ECS Mimamsa's Deep Thought. Thank you for attending.
So this was the end of the ECS Deep Thought. I hope I want to thank you everyone for being present here. I want to thank you Dr. Vinu Asla to be present here as a judge. He is also having a talk tomorrow at 7 p.m. in LHC on topic fostering critical thinking and engagement with the latest development in science and technology. Please be present there for his talk. It will be great experience. Now we are done for the quizzing events for the day. We will be having another session of Deep Thought starting from 9 a.m. tomorrow. 9 a.m. tomorrow we are having Biology Deep Thought. Please be present on time. This is for every participant. Please be on time. Everyone else also in audience, please be there for another Deep Thought also. So thank you so much. Now I request the teams to escort the team coordinators to escort the teams till the guest house. Okay, thank you so much. You guys can leave.